Welcome to a second video on limits at infinity. This video provides additional examples on how to determine limits at infinity that may be considered more challenging than the previous video. Let's go ahead and review the major ideas when finding limits at infinity. If we have the limit as x approaches infinity or negative infinity, where the numerator is a constant and the denominator is x raised to some positive rational power, then that limit will always equal 0. For example, if we had the limit as x approaches infinity of, let's say, 5 divided by x squared, this will equal 0 because our numerator is fixed at 5, and in this case the denominator is increasing without bound. So this fraction is getting smaller and smaller, approaching 0. Now the general guideline for finding limits at infinity of rational functions is to divide each term in the argument by the highest power of x in the denominator, and then we simplify, and then we should be able to find the limit at infinity in this new form. It's also true that if these limits equal L, then y equals L would be a horizontal asymptote. And this is helpful if we're analyzing the graph to help evaluate the limit. There are also three shortcuts for finding limits at infinity of rational functions. The first one states if the degree of the numerator is less than the degree of the denominator, then the limit of the rational function is 0. Here's an example of this case where if the degree of the denominator is larger than the degree of the numerator, the denominator is growing faster, and therefore this will equal 0. The second case is when we have the degree of the numerator is equal to the degree of the denominator, and if this is the case, then the limit is equal to the ratio of the leading coefficients. So here's an example where they're both degree 2, and the ratio of the leading coefficients is 5 to 2, therefore this limit is equal to 5 halves. And then lastly, if the degree of the numerator is greater than the degree of the denominator, then the limit does not exist. So if this has a higher power, this is growing faster than the denominator and therefore would approach, in this case, positive infinity, which does not exist. Okay, let's take a look at three additional examples. We have the limit as x approaches infinity of the quantity 2x plus 1 divided by the square root of x squared minus x. Let's take a look at the graph first. It's pretty easy to see from the graph that as x approaches positive infinity, this function approaches the value of y equals 2, and that is what this limit is equal to. But let's take a look at a couple other ways to determine this limit. The most general way is to divide by the highest power of x in the denominator. Well, we have an x squared in the denominator, so we'll divide everything in the denominator by x squared. But remember, this x squared is underneath the square root. The square root of x squared is equal to x, so when we go to the numerator, we'll have to divide by x. Again, the reason this looks different is because the square root of x squared is equal to x. So we are dividing both the numerator and denominator by the same value. Let's go ahead and simplify this. We would have 2 plus 1 over x, all divided by the square root of 1 minus, this would be 1 over x. Well, this approaches 0, this approaches 0, so we're left with 2 over the square root of 1, which of course is equal to 2. And a third way to evaluate this limit using this shortcut, you can think of this as having degree 1 because it's the square root of x squared, and this also has degree 1. So the ratio of the leading coefficients would be 2 divided by the square root of 1, which of course is also equal to 2. Let's go ahead and take a look at another one. Here we have the limit as x approaches infinity of sine 1 over x. Well, by now we should know that 1 over x is going to approach 0 as x approaches infinity. We have 1 over an increasing denominator, so this would equal the sine of 0, which is equal to 0. Or graphically, you can see as you approach positive infinity, this graph is approaching y equals 0, or the x-axis, therefore this does verify our limit. We should also notice that this graph does have a horizontal asymptote of y equals 0, which is the same as the value of this limit at infinity. Okay, let's take a look at one more. Here we have the limit as x approaches infinity of 5 divided by x minus arctangent x. So we should realize now that 5 divided by x as x approaches infinity is going to approach 0. So the real question becomes, what is negative arctangent x going to approach as x approaches positive infinity? And again, there's a couple ways to analyze this. If we were to graph arctangent x as we see here, it's pretty easy to see that as x approaches positive infinity, the function value is approaching pi divided by 2. So this would equal 0 minus pi divided by 2, which is equal to negative pi over 2. Remember that this x value here is the tangent function value, and arctangent returns an angle. So another way to think of the same thing would be to look at the graph of the tangent function, and we can see as the tangent function value approaches positive infinity, the angle is approaching pi over 2. So there are several ways to analyze this limit, and I think if looking at the graphs helps understand what these limits are equal to, it's a very valuable tool. And of course, the last thing we could do is graph the original function, y equals 5 divided by x minus arctangent x. But as you can see here, it's pretty difficult to see that this would be approaching the value of negative pi divided by 2. It's somewhere between negative 1 and negative 2, but it'd be very difficult to determine that exact value using this green graph. I hope you found these additional examples helpful. Thank you for watching.